Hi everyone, it's Mr. Canfield. Today we're going to be looking at something called linear approximation. So basically what we do with linear approximation is we're going to be able to use calculus, find the tangent line of something, and then instead of plugging in numbers to a difficult function, we plug in numbers to that easy to use tangent line and find an approximation of what the real thing is. So this says, there's some wording problems here. This should say use the tangent line of f of x is equal to the cube root of x at x equals 8 to approximate f of 8.1. So it sort of says it, but the language that we're usually going to see is going to say something like this. So I can plug in 8 here. The cube root of 8 is equal to 2. So that's possible, but then plugging in 8.1, that's not really something that we're gonna be able to figure out easily in our heads or by hand. So what we do is we use calculus and we get close to it. So the tangent line at x equals 8. So I already have the x and the y value, so I'll be able to say, y minus 2 is equal to something times x minus 8. And now I just need to find the slope, and the slope is going to come from the derivative. So if I take the derivative here, also I don't know if you can see the erasures here. I restarted this video. I really hated how I started it last time. So let's see. The cube root of x is the same as x to the 1/3. So I can say 1/3 x to the negative 2/3. So if I want the slope when x is 8, I'm going to have to plug 8 in here. So what's f prime of 8? Let's see, 1/3 times 8 to the negative 2/3, and 8 to the negative 2/3. Well, first I should flip it to make life a little bit easier. 8 to the 2/3. So 2/3, remember that's the third root, and then square it. So the third root of 8 is 2. Square it, we get 4. So 8 to the 2/3 is 12. Sorry, 8 to the 2/3 is 4, and there's a 3 down there. That's where I was getting 12 from. So we're getting 1 over 3 times 1 over 4, which is 1/12. And so we'll have a 1/12 here, and we've got our equation of our tangent line. But it says we want to approximate f of 8.1. Now, this is really what it's asking, but they wrote it in kind of a weird way. They say f of x is equal to the cube root of 8.1. And so what it's really saying is over here, when it says f of x is equal to the cube root of x, they're just showing, hey, we plugged in 8.1 for x. It's kind of an odd way to write the language, though. You'll generally see it this way instead. So here's the cool thing, though. So the nice thing is we've got this curve here, and here's the equation of the tangent line. If we go in, here's 8. At 8.1, the line and the curve look really similar. So if I plug 8.1 into this line instead of into the cube root, the output is going to be very, very similar. It's not going to be exact, but it's going to be very, very, very similar. And it's going to be close enough for us to do whatever we need to do with that number. So if I do y minus 2 is equal to 1 over 12 times 8.1 minus 8, and you might start to see why this is awesome. Why this is so easy. We get y minus 2 is equal to 1/12 times, wait a minute, 8.1 minus 8, that's 0.1. So 1/12 times 0.1, then we're just going to add 2 to it, and we're done. So 1/12 times 0.1, let's see, that's 0.1 is 1/10. I'm going to rewrite that. 1/10. So this is 1/120th. So this is going to be y is equal to 2 and 1/120th, which I don't know what decimal that is. I don't really need to know. Usually they'll give us nicer decimals than this to work with. But super great. Now this is the approximation, and the actual value is most likely not going to be that. So let's see. 2 and then plus 1 over 120 is 2.0083 repeating. Let's see what the actual value of the cube root of 8.1 is. So I'm going to do 8.1 to the 1/3 power. So notice it's 2.008, and then that 3 and that 2 are different, but that 9 rounds that 2 up to a 3. So they're equal to each other. Let's see, tenths, hundredths, thousandths, and then 10,000ths, they're only off by 1. That's incredibly accurate. So, or incredibly close. So, really, really nice. It's accurate to, what, 3 decimal places? So, fantastic. Using a calculator, find the error in using the linear approximation to f of x at x equals 0 to approximate the 4th root of e. Now, 4th root of e, let's think about this. This is e to the 1/4. So they're really asking us, right, the 4th root is the same as 1/4 power. So they're really asking us to plug in 1/4 to the exponent here. So, and we want to find the error. So the difference between the real thing and our approximation, we call that the error. Well, let's see. What is e to the 0? E to the 0 is 1, right? So let's use the linear approximation at x equals 0. And using it at x equals 0, we're using it because they told us to use it at x equals 0. We could have picked a different x value to start at. Linear approximation really depends on where you're told to start. And I think a logical question to ask after that, well, like on this last one, they told us to start at 8. Why am I starting at 8? Why do I want, well, because we want 8.1. Why am I starting at 0? Well, because I want 1/4. 1/4 is close to 0. 8.1 is close to 8. Usually what we're doing is we're taking the derivative at a number that's a lot easier to deal with, that's close to the number that we want. Usually it's just a whole number or an integer close to what we're looking for. So in this case, if I want the linear approximation, all I need to do is use the tangent line. So let's see, my y value was 1, and then m times x minus 0. Let's see, the derivative of e to the x is, e to the x. So then f prime of 0 is just e to the 0, which is just 1. So it's y minus 1 is equal to 1 times x minus 0. So I'm going to say y minus 1 is equal to x. So if I were to go in and look at that, so here's e to the x, and here's, I'll just have to add the 1 to both sides, x plus 1. So here's e to the x, here's x plus 1, and yeah, that's a tangent line there. So we're going to use that tangent line to approximate when x is 1/4. So if I do that, so we'll use our tangent line and we'll plug in 1/4 plus 1, that's 0.25, so 1.25, so y is equal to 1. So y is approximately 1.25. The approximate value, so, which this is approximately e to the 1/4. Or sorry, I should have said the 4th root of e. Let's see. E to the 1/4. Well, e to the 1/4 is actually 1.284, etc. If we were to subtract 1.25, then our error, the amount that we're off by, is 0.034. So error is, that's e to the, it's the 4th root of e minus that number. So that would be what we call our error. So there's this thing called error analysis where we're thinking about our error and we're looking at it. So if we were talking about money, and we were talking about approximations with money, you know, we're off by approximately 3.4 cents. That doesn't feel very good. I mean, yeah, if I'm talking about $1 billion and we're only off by a factor of 3 cents, like, okay, so we're basically there. But if we were talking about money, we would want to get our accuracy down to be less than, our error. We would want our error to be less than a penny. And so if we were going to do this, we would need to use a different value. But that's a story for another day. So let's see. For the tangent line to f of x equals x squared minus 3x plus 5 at x equals 4 to have an error of at most 0.1 in approximating f of 4 plus h, what is h? All right, that's a lot of words, but I'm going to go through and do my linear approximation model first. So linear approximation, first thing I do is I take the derivative. So 2x minus 3, and it says x is equal to 4, so I want 4, so f prime of 4. So that's going to be 8 minus 3, so it's 5. What about f of 4? What is that? That's 16 minus 12 plus 5, so that's 4 plus that's 9. Okay, so then I can say that I have y minus 9 is equal to 5 times x minus 4. And we want our error to be 0.1. This is kind of a tricky question. So, and jump straight into homework after this. So this is probably the first lesson we've had this year that I'm not a huge fan of how he's going through it. I'd like to see a couple more examples of linear approximation first, but it's okay. So we want an error. Well, the way the error worked was we would take f of, so like we'd take the actual number and we would subtract our approximation. So here I'm going to take f of 4 plus h, and then I'm going to subtract this. Well, let's see, y is equal to 5x minus 20 plus 9, 5x minus 11. So all I did here is I solved it for y and simplified it. I'm going to take this minus the y value we get, 5. And we're plugging in 4 plus h. So there's going to be a 4 plus h here for x. So we're essentially saying this, and we want our error to be at most 0.1. So let's set this equal to 0.1 and find out when that actually equals 0.1. So now 4 plus h into f of x is annoying. 4 plus h squared minus 3, 4 plus h plus 5. Like, that's what this is saying. I'd love to know what h was so we don't have to do all this. Now, I got to be careful in here. And that's minus 5 parentheses 4 plus h plus 11. So now if I square everything out, figure it all out, let's see, I'll get 16 plus 8 h plus h squared minus 12 minus 3h plus 5 minus 20 minus 5h plus 11. And I'm trying to get that to equal 0.1. Now, it says that I'm allowed to use my calculator on this question. At this point, before I folded everything out, I really should have just gone into my calculator. And I should have said, okay, calculator, I can do this algebra, theoretically. I've passed algebra, but I'd rather you do the algebra for me. So I'm going to write 0.1 in there. Then I'm going to do 4 plus x squared minus 3 parentheses 4 plus x plus 5 minus 5 parentheses 4 plus x plus 11. Like, this is, I can take this now and have my calculator find their intersection point using second calc intersect. This is a much more reasonable way for me to do this problem. So I'm actually having a really hard time seeing that. So let me zoom in. Oh, okay. So it looks like the highest, I mean, since 0.1 is the value that I care about, I should have my y value be 0, my y max be 0.2. Now I'm going to be able to see these intersection points a little bit better. So if I do this, now I'm finding my intersection points. First curve, second curve, guess. So I got negative 0.316 for H. Let's see what my other H value is. Intersect, go over here. So notice how, so here's the thing, if I go in between the two, it might go back to that other one and find the intersection point again. So I want to go over here, and I'm going to push enter over here on these. Now I know the first place it could possibly run into is that one. Oh, point. So these are my two possible H values where it equals 0.1, but I would like my error to be 0.1 or less. And so if I'm looking at this, if the curve is the error, well then anywhere in between those is going to be less. So I can actually say that H is between these three 0.16s, or sorry, 0.316. So you could say it's less than or equal to H, which is less than or equal to 0.316. So yeah, this ramped up quickly. I'm going to do another example from the homework. I know I don't normally do the homework, but I'm going to do this first homework question just because I want to make sure I'm giving enough help. Excuse me. So this one says f of x is equal to x squared minus 6x plus 12, x is equal to 2. Let's approximate f of 2.5. So I'm going to use x equals 2. So I already know it's going to be x minus 2. I need to find m. I need to find y as well. So I plug in 2 here. I'll get 4 minus 12 plus 12. Oh, the 12s cancel. So y minus 4. Okay, so now I just have to find m. So that's f prime of x is equal to 2x minus 6. So if I do that and plug in the 2, like I'm trying to find the slope. We're not doing 2.5 yet. We're focusing on the 2. So that's 4 minus 6 is negative 2. So negative 2. So we get y equals negative 2x plus 4 plus another 4. So I distributed the negative 2 and then I added the 4 to both sides. So y is equal to negative 2x plus 8. Okay. So using this, I want to approximate f of 2.5. All I need to do, plug in whoops, that's supposed to be a y there. Plug in 2.5, we'll get our answer. So I get negative 5 plus 8, I get 3. So an approximation of f of 2.5 when f of x is x squared minus 6x plus 12, an approximation is 3. So again, it's not going to be exactly 3. It shouldn't be exactly 3 because this is an approximation. It should be basically 3. In the same way that pi, why did I do that? Pi is basically 3, right? 3.14, it's basically 3. It's not exactly 3 though. It's basically 3. We're off by a quarter. Not perfect, but close. So in general, the closer the x value we're looking at and where we're approximating, the closer these are together, the more perfect our approximation is going to be, the closer our approximation is going to be. So, hope that was helpful. Have a great day. Canfield out.